My name is Mackenzie Hart and I'm the project manager of SPEAR. SPEAR has existed now for 2 years. We spent the first few months optimizing a team organization that would be best for designing and building a competitive rover for the URC. SPEAR is split up into its design and administration teams. Administration organizes our academic outreach programs, financials, events, website, and social media accounts. The design team is organized into mixed discipline teams that each work on a subsystem of the rover. SPEAR has been able to earn the support of its community. Through sponsorships, grants, and funds, we currently have more funding than necessary to finish building our rover, go through rigorous testing, and be successful at competition. We followed a modern design process where we spent a majority of our time ensuring our designs were well thought out with many internal critical design reviews. Each were assessed by our academic advisor. Each system and part of our rover has been designed to perform every task in the URC with a reasonable factor of safety. In preparation for the competition, we are working with the U of A to use spaces on campus to test our rover systems to their maximum potential. We have accurate Martian soil for our probes and drill testing, accurate Martian environments to test extreme driving capabilities, a lab with rigs to test each of our mechanical systems' durability, and different objects to test our arm and hands capabilities.
One of the major design decisions that we made with regards to the arm was the decision to use 5 rotational actuators, 4 stepper motors, and 1 brushed, in order to provide us with more flexibility to move the arm. Another element that we introduced into the design was a hanging hook located partway between the elbow and the wrist, which allows the arm to minimize the orthogonal distance between itself and a heavy load, such as in the extreme retrieval task. At the wrist, there is an attachment that allows a hand or an auger to be switched using a chuck. This allows the arm to accomplish both the soil extraction and equipment servicing task with minimal work required to switch between the 2 modes.
Our big focus so far has been the suspension system, specifically the differential bar. We are in the process of testing its range of motion and its capabilities in helping the drive system overcome a variety of different terrain. The rocker bogie system is comprised of 2 links on either side of the chassis, which acts as the legs of TARS, where the bogie link connects to the rocker link in such a way that the connection is a pivot for the 2 front legs, and the top of the rocker link acts as a pivot for the rocker bogie assembly.
So we looked at lots of different designs for the differential and ended up coming up with a simplified design for the rocker bogies to be able to be linked together, to have one go up and the other one come down.
We're trying to make the chassis as simple and light as possible while confirming to the rocker bogie system's requirement of having the center of mass at least 20 centimeters from the front of the rover. We're getting that done by using T-slotted aluminum beams. They're lightweight as well as inexpensive and really easy to disassemble and reassemble. So that makes iterative design super easy. We're designing the bearing mount on the chassis to withstand at least 2,000 newtons. We're pretty confident that it should be able to withstand almost all the terrain traversal tasks. Of course, we're going to confirm that through testing.
So the biggest part that I wrote about in the SAR is that software is on board every part of the rover. So this includes on board the arm, on board the drive subsystems, on the communication from our home base to the rover, as well as the autonomous and science subsystems. So this is a lot of software and a lot of different parts. So essentially what we did is all of our software team, we worked flexibly throughout the team. We use the ROS meta operating system, as well as C++ and Python for all of our code. And all this code kind of works together very well and is able to control all of the operations of our rover.
We identified the 6 major elements that are, for the most part, required for life. And that is oxygen, hydrogen, nitrogen, phosphate, sulfur, and organic carbon. Our bench tests are focused on locating these 6 elements. So we're doing a soil test to look for nitrogen, phosphorus, pH, and potassium. We're going to locate our sample site by using temperature and moisture sensor, a UV sensor, and an IR camera. By doing this, we can find anomalies in the ground in order to figure out where bacteria is most likely to collect, and taking a sample based on that.
We have a great group of people that are passionate about this project, which is why we have been so successful for being a student group that just got started a year ago.